Greetings, folks. It's Professor Fiore here. And what we're going to do right now is take a look at the high frequency performance of a current-controlled current source. In other words, an op-amp-based current amplifier, such as this. I want to take a slightly different tack on this in this video. And that is, instead of just sort of grinding through and developing some equations and things like that, and then verifying them with the simulator, I want to look at this in a more open-ended sort of way. What do you do if you don't have a pat answer somewhere? How do you figure these things out? Right? I don't like to just throw equations out and sort of say, trust me, they're correct. You should be able to understand where they come from, replicate them, things like this, right? That's where we turn information into knowledge. So, here we are faced with this current amplifier. How do we determine the frequency response? Well, the first thing is the low end, F1, is easy because, the op-amp itself is direct coupled and there are no capacitors in this circuit. Therefore, F1, the low frequency limit, is 0 hertz, DC. It's directly coupled. It's done, right? That part is done. But what about F2? The top end, how high up in frequency will this amplifier go? Now, we've already done this with voltage amplifiers. And if you haven't looked at the F2 calculations, the gain bandwidth calculations for non-inverting and inverting amplifiers, you should take a look at that first before going through here. You should also take a look at the video on current amplifiers in general. Right? The just general operation of this kind of circuit. So no biggie, you can just pause this, put it down, pick it up again after you watch those, right? All right, so I'm going to assume that you already understand how this amplifier works. We derived an equation for it. We said the current gain is equal to a negative, because it's an inverting amplifier, 1 plus Ri over Rf, right? So the current that's produced in the load will be independent of the load resistance. I could have 10 ohms in here like this, or a K ohm, 57.3 ohms. It wouldn't make any difference. We're going to take an input current, multiply it by a certain factor, and that's going to produce an output current. The end. Within the normal limitations of the op-amp, right? You can't expect the op-amp to be pumping out 10 amps. It's not going to happen. But within those sorts of limitations, we just have this one equation, right? And this particular circuit, Ri happens to be 9K, Rf is 1K, so 9K over 1K, 9 plus 1, 10. We should have an inverting gain of 10 out of this thing. And of course, 10 in decibel form would be 20 dB. All right, great, fine. The F2 part of this is kind of up in the air. For voltage amplifiers, inverting or non-inverting, we determined that the upper break frequency, the 3 dB down point, was the F unity of the op-amp divided by the noise gain. And for either of those circuits, the noise gain was equal to Rf over Ri plus 1. Happens to be the signal gain for the non-inverting amplifier. It's the magnitude of the signal gain plus 1 for the inverting amplifier. All right, so I look at this and I say, well, how does this correspond? I mean, there's something called Ri and something called Rf, but they're really only called that because Ri is on the input end, right? And Rf is over here, further into the feedback loop. They could be called R Larry and R Mary for that matter. It doesn't really make any difference. What's the sensibility of this? Am I just supposed to use the gain of the amplifier? The gain is 1 plus Ri over Rf. Use the magnitude of that. In this case, 10. Would that be appropriate? Is there something else going on? If you look at this, you realize that the positions of Rf and Ri in the voltage amplifiers, those don't exist here. Rf and either of those voltage amplifiers went from the output of the op-amp back to the inverting input. And the Ri, if you think of a non-inverting voltage amplifier, right, the Ri goes from that same point, the inverting input, down to ground. Okay, I've got a resistor on the the inverting input, but it's not going to ground. I don't have a single resistor going from here to here. How does this match up? Well, it doesn't. So how do I find a noise? What's the deal, right? Well, at this point, we're going to use scientific method. I'm going to just kind of come up with a hypothesis from what I've already determined elsewhere and run with it and see what we get. And if it doesn't work, we'll modify it. Try that. If it still doesn't work, maybe we'll just dump it and try something completely different. All right. We're not just, swinging around here in the dark. We have, existing knowledge. So let's use that. Let's leverage that, right? This is not a random process where, hopefully we'll just hit on the answer. Not doing it. All right. So, where do we begin? Where's a logical place to begin? Well, I think a logical place to begin would be just to kind of notice the similarity between these two equations, right? And say, well, maybe it's just the gain of the amplifier, like it kind of was with the series parallel non-inverting amplifier. Let's try that. All right, so the first thing we need is the F unity. So a TL071, that's about a 3 to 4 megahertz. Let's call it a 3.5 megahertz amplifier for an F unity. So if this hypothesis is correct, then, like I said, the gain on this is 10, inverting gain of 10, 20 dB. So I would expect an F2 to be somewhere in the 3 to 400 kilohertz range, right? It's F unity divided by 10. So if that's 3.5 meg, then I'm going to expect an F2 of about 350 kilohertz, okay? All right, so let's just try it. So we're going to come up here and do an AC analysis. We'll do, a Bodie plot like usual. See what we get. All right. Bring this over. Open it up so we can get some accuracy. So the first thing I notice is the gain, right? So the gain on this, get over there. So the gain on this, like we said, is 10 or 20 dB. So that's what we're seeing right here. Right down here in the pass band, we're getting 20 dB, looking good. So I'm going to have to go up to a 3 dB down point, in other words, where it hits 17. What is that? 18, 17. Wah, 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 wah. Okay, well, we'll call that 17, right? We're getting 3.475. Call it 3.5 megahertz. Well, that's not right. That doesn't work compared to, what we were expecting. That's 10 times bigger. I mean, that basically is the F unity of the amplifier. Hello. What's the deal there? Okay. All right, so I know that's not right, but let's poke around a little bit. Maybe this has something to do with the RI and the RF, right? Here it's RI over RF, here it's RF over RI. So if it was the other way around, right? In other words, if it was 1 plus 1K over 9K, that would be about, a net gain of 1 and a ninth. So, about 1.1. And in a case like that, if I had F unity divided by 1.1, yeah, I would get somewhere around 3.5 megahertz. That would be sensible. All right, so that's my hypothesis. I'm just going to assume maybe those are flipped. So I'm going to come in here and change my RI to 1K. Why? Because with 1K and 1K, it's not really going to make a difference which one's on top. It's going to work out to be 2 either way. All right, so, 1K over 1K or 1K over 1K plus 1, gain of 2. So if I have a gain of 2, I would expect my F unity divided by 2 to be somewhere in the 1.5 to 2 megahertz region. Maybe 1.7, 1.8, something like that. Let's see. What do you think is going to happen? Badunk. All right, so our gain did go down to 6 dB, right? Because it is a gain of 2 now, so that's great, right? 6.02, which is the exact value. So we need to drop down 3 from that, or just about 3 dB. Come on. Right. Okay, that's close enough. 3.5 meg. Ow! That didn't work. Oh, Marge, what'll we do? So 3.5 meg. You know, here we are. We're still at F unity. That's what I got last time, right? I mean, the passband gain changed, but the break frequency didn't really, right? This was nearly 3.5 meg, and this is just a smidge over 3.5 meg. You know, between the accuracy of moving this cursor, we got no change, right? We have no change, really. So, all right, that's history. It looks actually like the gain, at least the value of Ri, is not making any difference here. So I'm going to go back to this original value of 9K. All right, so we've changed. We have two different gains now, and we get the same exact value. Right? All right, so what's next? Well, the one thing I did not change over here was our load. So let's try and change our load. Maybe that would have an impact on the frequency response. So I'm going to bring that up to the value of RF. You know, I don't want to change this just a little. You know, it might be too subtle of a change. So I'm going to bring that up to 1K. So they are the same size. This should still give us the gain of 20 dB. Right? I haven't changed from the original, the Ri and the RF. Let's see what happens. Boom. Okay, there's my 20 dB. So we're back to where we should be. Now we got to find 17. Right around there. Ooh, look, we're like 1.6 and change. Right? Depending on how far we want to take this. 1.66. So nearly, you know, nearly 1.7 megahertz. Ooh, now we're talking about something. So that basically cut this in half. In half. I didn't change the gain. That was still 20 dB, but the F2 basically got cut in half by making our load bigger. So what's the next obvious thing to do? See if we've got a trend, right? So I'll make that 10K. Now, again, my gain is still 10, right? It's still 20 dB, but I've increased my R load considerably now, right? So now it's 10 times bigger than RF. Let's see what happens. Will this trend continue? Will the F2 continue to decrease? Will this continue to narrow? Still have the 20. Go find 17. Right around there. Hey, we're at 275. Wow. That's pretty interesting. So that's dropped considerably. All right. I mean, that's a factor that's more than 10, right, compared to the original value that we had. So what the heck is going on here? All right. Well, we can keep coming in, you know, coming in here and poking around with different values. And you will notice that there is a nice continuation that happens here. All right. You will notice that as the R load grows, keeping these other resistors constant, this F2 keeps getting smaller and smaller and smaller. So it appears to be the effect between R load and RF. That ratio seems to be doing something. All right. In fact, it turns out that it is really this ratio, R load to RF, that you're going to use for a noise instead of the feedback resistors. Now that sounds a little strange. You know, it's not the gain of the amplifier, right? It's not the current gain that affects F2. It is in fact the ratio of the load impedance, the thing you're trying to drive, and this one feedback resistor. Now, if you scale the gain by changing both of these, what really matters is, again, this RF compared to this R load, right? So just to make your life a little easier, I'll just write it like this, okay? So it's still F unity divided by AN for F2, but now we find AN is R load divided by RF, all right? So you can see when our load is only 10 ohms, our load over RF is, you know, it's a fraction of a value. So your AN is just a smidge over 1, and consequently your F2 is F unity. When we set this to 1K, 1K and 1K, that gave us a noise gain of 2. So we had the F unity divided by 2. So 3.5 divided by 2, 1 3/4 megahertz, which is about what we got. And then when we ran this up to a higher value, ran this up to 10K, well, we had 10K over 1K plus 1. So that's a noise gain of 11. You take your 3.5 megahertz, you divide it by 11, and now you're down, in the 300 kilohertz range, which is, again, around where we were. All right. So, not remembering the exact values, but that was the trend that we were seeing. And you can, like I said, replicate, just build this circuit and just start putting different values in, and you'll see the trend. So here's the kicker, though. Why? It's one thing to go through this and say, well, this is what happens, but why? I'm never one to just have you memorize something. I want you to understand why these things occur. What is it? How do we find noise gain? Well, it may not be immediately apparent, but you can do a delta Y conversion on this thing and come up with something that looks like, at least when it's simplified, looks like the series parallel configuration that we use for a non-inverting voltage amplifier. So from your circuits analysis, right, from that study, you might remember the delta Y conversion. You have this, right? So here's the Y configuration. Here's the delta configuration. It's actually an upside down delta, right? It's supposed to be like a triangle, right? And sometimes they call this a T, sometimes they call this a pi, right? But basically, this is your delta, this is your Y. So right now, the configuration that we have is this Y configuration, right? There's 3 pins, X, Y, and Z, right, on both of these. And if you remember one thing about these conversions, once you do the computation, the delta is the functional equivalent of the Y and vice versa. You can replace any Y with a delta that's appropriate. You can place any delta with an appropriate Y. And the rest of the circuit behaves the same way. So we have this configuration, right? Y is the op amp's output pin. Z is the system ground, and X is the inverting input. So let's go back to the circuit. Right, you can verify this. Right, so here's your 3 resistors. This is the Y, or the T. Okay, so output of the op amp, ground, inverting input of the op amp. So you take these 3 things and we do the conversion on it. Right, we get something that looks like this. So here's what's going to end up happening. If this is the output of the op amp, you're going to have a resistor, this RC, which goes from there to ground. Actually, we don't even really care about that. More importantly, I have a resistor that goes from the output of the op amp back to the inverting input. And from the inverting input, I have a resistor that goes to ground. Well, you know what? I've just described, right? Here's a resistor going from here to here, and a resistor going from here to ground. That's the exact configuration I have when I go to find the noise gain of my series parallel non-inverting amplifier. And actually, when we simplify it, we get the same thing out of an inverting voltage amplifier. So guess what? If you were to come in here and do the conversion of these resistors, right? You take the 3 resistors that we have currently. So this is your Ri, this is the RF, and this is the R load. You convert them into this. Use these equations, right? These are in the DC circuits book. You use these equations to find the RA, the RB, and the RC. Right? What you really need is the RA and the RB. The RA is in the RF position, right, for a non-inverting amplifier, and RB is in the RI position of that same amplifier. So you would figure out the RA and the RB, and then you would just take their ratio plus 1. That's your noise gain. Okay? Now here's the really cool thing. If you look at these equations, you will realize that you don't actually have to compute the precise values of RA and RB. In fact, it turns out that the ratio of RA to RB in this delta is the same value as the ratio of RE to RF in the Y configuration. In other words, the ratio of the R load and the RF. So I don't actually have to compute RA and RB. I'll get the same value. I'll get RA over RB just by taking RE over RF, right? And where RE is the load, and we go from there, right? In other words, RE is the load, and RF just happens to be RF. How convenient was that, right? So there you go. You can grind through this. You can try it. Right? You can take these values, throw them in those equations, and you'll see that, yeah, you will always get the same ratio. The ratio always works out. The numerators of those three things are identical. So it's really the denominators that matter. And then when you do a little algebra on it, you realize it'll always work out to this. Okay? So, boy, does that make things a lot easier, right? I just have to take my R load and my RF, take the ratio, add 1. That's my noise gain. Divide that into the F unity, and I've got the F2. Oh, geez. You got to love that. All right? All right. Not immediately apparent. But, what we're doing here is a little bit of a very, very small, right? Admittedly, a very modest version of the scientific method. We're starting up with an hypothesis that we base on things that we already know, right? Observations we already have. Try it. Didn't work. We modified it. Still didn't work. We abandoned it and went to something a little bit different. Tried it. It worked. Now, of course, that by itself isn't sufficient. We're gonna keep trying over and over and over and over again, right? Every success that you have is like a layer of varnish right on a piece of furniture, and it just gets to the point where you just have so much evidence, you got it, right? One thing that kills it, one thing that doesn't work, okay, you got to go back to the drawing board. But we go to the next level, of course, and we look at the basic theory. In this case, we can look at the delta Y conversion, and we come up with a good theoretical model of why it should work out this way. Okay, great. So I hope you've pulled something out of this beyond just, what is the upper break frequency of a current-controlled current source using an op-amp. Hopefully you've gotten a little bit more out of this, right? It's a good lesson. It's a good thing to sort of play around with. All right. Okay. So as usual, any questions, put them down in the comments, right? And I hope you have a good day. Take care, and we'll see you next time.